once we have robust and scalable, large-scale quantum computers, what happens next when we start interconnecting them the way we did with classical computers? And is that going to open up something really, really new and cool and exciting the way it did with classical computers? So this leads in, it sort of sits at the intersection of communications and network theory and quantum computing, but I'll try and do it without too much technical detail. And now, if you want to ask a question, just interrupt and talk over the top of me, because I'm on a different screen now and I won't necessarily see the chats come up. So is that showing okay?
Yep, looks great.
Yeah, okay, brilliant. Okay, so this is what we're going to be talking about, the quantum internet, which is sort of the next generation after quantum computing. And it begins with this question: what happens if I take two quantum computers and add them together? Or let's take it back a step and just say, what happens if I take two computers and add them together? Well, if it's a classical computer, we know that you take two classical CPUs and you put them together, what do you get? You just get twice as much computational power as what you started with. So you can network them together and make like a cluster. That's really how supercomputers work. You just have commodity hardware and you link them all together. What about if it's a quantum computer? Is it still just you add one and one together and you get two? Well, the answer is no. And that's exactly why quantum computers are exciting, is that with classical computers, the power, the computational power is really linear with the number of CPUs or the number of constituent blocks that you have within it. With quantum computing, that's not the case. With quantum computing, we know that the power of a device can, in principle, for certain applications, grow exponentially with the number of constituent parts. So this nonlinear relationship means that 1 + 1 is actually much greater than 2. So we get something which is greater than the sum of the parts if we were to be able to unify them into a joint device. And so this is really what we're angling at with this talk, is what are the implications of these links here that allow us to connect quantum devices together. So in a classical context, the way that people distribute computation is usually you have a server node in the middle. So your phone sort of dials into a central server at the AWS platform, and then it might distribute threads out across a whole bunch of child nodes, and they do some computations, and then they send the results back in, and it gets conglomerated and then sent back to your phone. Now you can do the same thing with a quantum device. The only difference is that these aren't classical communication links anymore, for obvious reasons. In other words, we're not just communicating bits of digital information, but instead these have to be quantum channels which allow for qubits to be transported. And we're going to specifically focus on what are called entanglement distribution links, where the purpose of a link between two quantum devices is to distribute an entangled pair of qubits. And in networking, well, obviously we're going to be talking about light usually. So photons, for example, we want to distribute an entangled pair of photons between our server node and our client nodes so that they can act in a unified way according to quantum principles rather than classical ones. And then we sort of have the same principle, that all of these are able to act collectively as a single unified device, which has much greater power than the sum of the individual parts that belong within it if they were just operating independently. So what is entanglement? Now, I don't know exactly how much of the maths and that kind of thing I heard you guys talking about doing vector transformations. So that fits neatly into an elementary description of what entanglement is. So I'll show you what I promise will be the only mathematical notation that I'll use in this talk. If we're talking about photons, then I'm sure you all know that photons have polarization. So if the photon is traveling in this direction, then the polarization angle refers to the transverse angle at which it's oriented orthogonal to the direction of propagation. That's what your sunglasses do when they filter out half the light. They just filter out one of the polarization axes. So for photons, you might imagine that you can have horizontally, or other way around, vertically polarized photons, horizontally polarized photons, but you can also have any angle in between. We call this the diagonally polarized photon, D or plus. You can also have one going down here, which we call the minus state. But you can have any angle in between. And as you'll discover when you do your vector transformation, these angles can actually be represented as complex numbers. So it's not quite just a two-dimensional plane. So the mathematical notation that we can use to represent the state of a single photon, we represent it using this notation called a ket notation. So you write this symbol, it's a right angle bracket, and inside you write what the state is. So you can have a horizontally polarized photon, a vertically polarized photon, or a diagonally polarized photon, or the down diagonally polarized photon. But you can also have superpositions. So for example, you can make a superposition of horizontal and vertical, and that's represented using the symbol plus. That just means that it has both of these components simultaneously according to some amplitudes. Now, that's what a superposition is. Entanglement is when you have a superposition across multiple particles. And the standard one that people consider is usually what's called the Bell state, where you have a superposition of H and H and V and V. So the way to interpret the meaning of this state is that this represents the state of the first photon, so does this one. This represents the state of the second photon, so does that one. And so you see that we've got a superposition whereby the two particles exhibit properties of being both horizontal and vertical, but it's not determined. It's this ambiguous state, but they're guaranteed to be correlated nonetheless. So that's really what entanglement is. It's when you have a correlation, but it's in superposition form as opposed to a probabilistic form, the way it is in a normal computer. So what this means is that if we go in now and measure the first photon, the second photon is guaranteed by that correlation to have the same state as the first one. So if I measure one photon and it's horizontal, the other one is guaranteed to be horizontal as well. Similarly for vertical. And these entanglement states are really, really useful for all manner of things, and including cryptography and including this problem that I mentioned before of joining multiple discrete quantum devices like quantum computers together to make them behave as one. Cool. Now, if we've got a quantum communications link that we want to use to connect to very remote quantum computers, they might be thousands of kilometers apart or something like that. In a normal classical communications link, just like an electrical wire, well, we all know how that works. You start with one party, Alice, and you send your bit of information, which is 0 or 1, as an electrical signal, and then it arrives on the other side. So we just use direct transmission to communicate normal classical bits. Would we do the same thing with quantum information? Suppose I had an arbitrary quantum bit now, so this is a qubit, and I want to transmit it from A to B. Would I do the same thing? Well, you certainly could. There's no denying that. But it turns out that that's actually not a very optimal thing to do. And the reason is because quantum information is subject to some constraints that classical information isn't. If I give you a bit of classical information, a 0 or a 1, whether it's written on a piece of paper or it's encoded into an electrical signal or an optical signal, in any case, you can measure it and then you can replicate as many copies as you want. In other words, suppose that this is an optical fiber channel, and all of a sudden this fiber is lossy and some of the light doesn't get through and it doesn't make it to the other end. Well, you can just reproduce the bit that you started with and send it again. So you just repeat it over and over again. That's exactly what our normal communications links do. If something fails, we just try it again. With quantum information, actually that's prohibited, not by any engineering obstacle, but by the laws of quantum mechanics itself, by what's called the no-cloning principle. And what that means is that if I give you an arbitrary quantum state, so I'm not going to tell you what it is, I'm just going to give it an arbitrary unknown label, it is, by the laws of physics, impossible to take that and produce two identical copies of the same state. So if it's a known state, in other words, I tell you in advance that it's either 0 or 1, then yes, you can do the normal classical thing of just measuring it and reproducing as many copies as you want. But because of the superposition principle and the fact that when you measure a state that's in a superposition, that it collapses down and eliminates the superposition, you can't actually replicate that arbitrarily. So going back to our qubit, if our channel was lossy here and we were sending a photon as a qubit and it got lost, well, boom, it's gone. We can never get it back and we've lost valuable information. So we don't want to use the classical approach of just transmitting and over and over again until it works, because we can't. We don't even have that option. So instead, what we do is we use a different approach, which is called quantum state teleportation. And what we do there is we utilize entanglement to bypass this problem. And the way it works is this. So I have an entangled pair. So they come from a single source. This is my, for example, HH plus VV state here. Then I have my, yep.
Yeah. Before you go on, it might be good to answer the couple questions that come up.
Yep, sure. I'll just have to quickly switch back to the other screen.
Sure.
And then I can read it. Awesome. Okay, are we looking at Miles? Oh, yes. Yeah. Oh, okay. Okay, so superposition just refers generically to the idea of having a state which has multiple possibilities at once, whereby it's simultaneous as opposed to probabilistic. So, you know, if you flip a coin, it's also not determined what the outcome is, but it's actually deterministic. It's probabilistic. You just don't know which one it is. Whereas for quantum information, superposition means that it genuinely has both states at once, and it's not revealed until you measure it, and then it collapses down. Entanglement is exactly the same as superposition, except that it's in a multi-qubit or multi-particle context, whereby you have a correlation which is distributed across the superposition. So like the one I said before, it's not determined whether a photon is horizontal and vertical, but they're guaranteed to be correlated nonetheless. That's the difference. Okay, I'm looking at Maggie now. Oh, great. Sorry, Maggie, would the number in front, both of them be the same? Oh, by number in front, I assume you mean the amplitude in front? I've sort of, yeah, I've left out the, I've just been a bit sloppy and left it out. So actually, yes, they do have amplitudes and they can be arbitrary numbers. So I'll go back to the other screen. So for example, you can have a state alpha H plus beta V, and these alpha and beta can be arbitrary complex numbers as long as it satisfies a normalization constraint, which ensures that the probabilities add up to 1. So specifically, the rule is that the sum of the absolute square of all of those coefficients has to add up to 1, and these give you the probabilities of measuring those respective states. But it can certainly be anything. Now, modulo leaving out those numbers, that's our entangled state in general form. Here we've got our arbitrary unknown state. And imagine I want to get that state from there down to here. This is point A and this is point B down here. Instead of transmitting it straight down like that, what we're going to do is do an entangling measurement on these two qubits here. An entangling measurement is one where it's just like the opposite of preparing an entangled state, whereby you measure it in a way such that instead of asking what is H, is a single qubit in the state H or V, we're saying what is the correlation between them. We can talk about that a bit more later on, but you can implement this when you come onto quantum gates using a CNOT gate and two individual single qubit measurements. Now, forgetting about the details of what goes on in here, when I do that entangling measurement, and then get some classical outcomes, which I feed forward down to B to do some little local corrections down here, then all of a sudden this state up here magically appears down here. Even though there is no actual quantum communication taking place across that divide. We're only communicating classical measurement results, where our detector says you got this result or that result. And so this is really interesting. We've made quantum information that was up here appear down here, crossing a divide where there was no quantum communication taking place, but it was mediated by this entanglement that was shared between them. And so that's called quantum state teleportation. It's got nothing to do with Star Trek type teleportation. People in the mass media often try and allude to that, but it's got nothing to do with it. So why would we communicate quantum information like that? Well, the reason is that this down here, this entangled state, is a known quantum state. It's just HH plus VV. It's always the same. So I can reproduce as many copies of that as I want. It's not subject to this no cloning limitation that I mentioned before, because it's not an arbitrary state. It's a well-defined and known one. This one, on the other hand, is our valuable one, where we can't make arbitrary copies because we don't know what it is. So we shift all of the repeat until success side of the protocol down to distributing the entanglement. We distribute that over and over again. When we finally succeed in distributing entanglement across our network, however many times that takes, when we've got it, then we use that to complete the teleportation protocol, and the actual quantum state of interest bypasses the quantum channel altogether. And so that's the way we're going to do things in quantum networks, rather than transmitting quantum information directly, or at least not the valuable quantum information. Okay, so we know that we're interested in distributing entanglement now, these states of the form HH plus VV. This is sort of a really valuable resource to us, because we can teleport things and do all sorts of other applications with it, connect quantum computers. How do we go about distributing entanglement across a network? Well, there are a bunch of things that we can do with entanglement that we can't do with classical information. Suppose I've got two entangled pairs. I'm going to represent them like this. The edge here represents entanglement between these two qubits. So this is qubit 1 and this is qubit 2. And suppose I want to get entanglement between A and B, but I don't have a direct line of sight from A to B. But I've got entanglement between this point here and this point here, and this point here and this point here. Entanglement swapping means that I can take these two qubits in the middle and do one of these entangling measurements that I mentioned before, which is a joint 2-qubit measurement that measures the correlations rather than the individual qubit values of the single qubits. If I do that entangling measurement, it destroys these two qubits and leaves these two entangled. And now I have entanglement between those 2 points. And this is another one of those weird quantum phenomena, because these 2 points, A and B now, they never directly communicated with each other. There was no transfer of any kind of quantum information directly between points A and B. Instead, we have some entanglement source that distributes entanglement between this point and this point, and between this point and this point. These guys never communicated with each other at all. Then along comes some guy in the middle, does something magical through an entangling measurement, and all of a sudden that entanglement hops across and ends up between A and B. Obviously, this is something that you can't possibly do with any type of classical information, but you can see that this is going to be useful in a quantum network because now I can try all of these individual parts within the network independently. When I finally get an entanglement link between these two, and then finally get one between these two, I swap it, and all of a sudden I end up with entanglement between these two. So that's entanglement swapping. That's one of the building blocks that we're going to be using in our entanglement network. And the next important one is called entanglement purification. Just like any sort of information, when you transmit it over some distance through whatever means, you pick up noise. This happens to electrical signals. You get degradation in the signal quality. Now, with electrical signals, in fact, all of our contemporary digital information, it's all digitized, whereby you imagine that if you have some voltage level, you just arbitrarily say, well, a 0 corresponds to having this voltage, 0, and a 1 corresponds to having this voltage. And what happens if my voltages pick up noise through the network and it actually ends up down here or wobbles around a bit? Well, the point of digitization is we just draw a dividing line between the middle, and as long as it's above, we say it's 1, and as long as it's below, we say 0. So it acts as a sort of error protection mechanism, this digitization, whereby you snap things back to the closest discrete value. That's exactly why we use digital computation instead of analog computation. So what about quantum information now? Because quantum information isn't strictly digital like this. It has all this superposition structure and all this entanglement. Does it obey the same properties? Well, no, it doesn't. It is kind of analog in the sense that the amplitudes in front of these different components in the superposition, they can be arbitrary. So it can be thought of as a generalization of analog information. So the simple digitization trick doesn't work. How else can I go about improving or reducing the noise and making it more robust against noise as it propagates through the network? We use entanglement purification, whereby we take 2 noisy copies of an entangled state. So this is one of our HH plus VV states, and this is another copy of it. And both of these have been subject to noise. If I do appropriate operations on those 2 halves, what it does is it destroys 1 qubit from each side, leaving the other one intact. And then this one has less noise than either of the 2 individual ones here or here that we started with. So if this was a noisy channel, this was a noisy channel, I chop the number of entangled pairs I have in half, 2 becomes 1, but that one remaining has much less noise than either of the individual ones. So you can see that that's going to be useful. Now we have a method to use things like entanglement swapping to build up a lot of distance across a network. And we can use entanglement purification to take many copies of that and collapse it down to start increasing what's called the fidelity, or in other words, reducing the amount of noise associated with this final ball pair. And you can do that as many rounds as you want. You can do this as like a hierarchy. You take 2 copies and you reduce that down to 1 copy, and you take another 2 copies and you reduce that down to 1 copy. And then you take those 2 and you reduce that down to 1 copy. So it's now we've done 2 rounds of this process, and each round of this, you boost up the fidelity of the state that we're dealing with. So
do we lose, I'm sorry.
Yep.
Do we lose any information when we destroying this channel? Is there a lot of information that is useful for our algorithm when we are making a less noisy channel out of 2 channels?
Sorry, so what was the question? If we're making a less noisy effective channel out of
do we lose
copies?
information? Do we lose
lose information?
Yeah.
No, not in this context, because all of these are in principle meant to be the same state. All of these are identical copies of the HH plus VV state. So they're not arbitrary states. So they're not really carrying the information that's of interest to us. They're all identical, but have been subject to some noise. So really the idea is then that at the end, we have exactly the same state that we started with. It's just that whatever that noise is less. However, then if you go and take this final state and put that through something like the quantum state teleportation network that I mentioned before, then what that means is that my state here at the input, it arrives at the output with more of the original information content from beginning to end. In other words, it's lost less across the channel. The quality of this entanglement directly reflects the quality of the state that we teleport using the entanglement. So there is an equivalency like the one you just stated, that effectively this is tantamount to losing less information as we complete teleportation. Does that answer that question?
Yes, yes.
Okay, cool. Okay, so let's have a look at what people are actually doing with this. A number of you might have read, there's a big headline article recently about the Chinese with their quantum satellite. I've drawn here a bunch of them, but they've only got one, and only it's the most that we're going to have for a little while for reasons I'll go into. But the Chinese do have a satellite that does entanglement distribution across about 1,500 or 2,000 kilometers between two very distant base stations in China. And so they have one of these satellites in space, and what it does is it produces one of these HH plus VV states, where these are single photons now. So one photon goes down this way, one photon goes down this way. And even though it's not reflective of my map, these are two different points in China, about 1,500 kilometers apart. One's up in Tibet at high altitude so that there's less atmospheric loss. And the other one is quite a distance away. And so this thing just spits out many, many copies of these at a rate of about a gigahertz or several hundred megahertz, so hundreds of millions to a billion per second. And then they come down and with all the atmospheric loss that takes place, what you end up is receiving those two photons at the base stations at a rate on the order of sort of hertz levels. So you reduce a preparation rate of on the order of a billion a second. By the time it gets through the atmosphere, you're picking up a few clicks per second. That's how much you lose across the atmosphere. But they've successfully done this, believe it or not, and using that have done some experiments proving unambiguously that you do get genuine entanglement between those distant locations on the ground. Now, at the moment, there is only one satellite. You can see that the obvious long-term objective is more along the lines of what I've got drawn here with a constellation, whereby you might have an alternating sequence of bell pair sources, like this one could be a source, and then this one could be a source, and then this one could be a swapper. So you spit out these entangled pairs here and here, you spit them out here and here. Then this satellite in the middle does this entangling measurement that swaps the entanglement across so that now we've effectively got entanglement between here and here. And by having an alternating sequence like that, you can wrap around beyond the line of sight of what a single satellite would be capable of reaching. And so the long-term goal of this kind of project is to work towards something like that, whereby the world can have a constellation of quantum satellites that in principle allow point-to-point entanglement to be accessible anywhere on two different points on the Earth. But that's a long way away, because this swapping is not so easy, because it requires all sorts of synchronization problems. And it's going to be quite some time before we get past the simple demonstration we have at the moment, where it's just a single satellite hitting two different base stations. Of course, you're not restricted to satellites. People can do it using fiber as well. The Chinese are also the leaders in this, where you have just fiber links across the ground transmitting entangled photons. And certainly a real long-term quantum networking infrastructure will be a hybrid of all these different technologies, where at smaller ranges you might have fibers, at longer ranges where you have to wrap around the earth you use satellites, just in the same way that we do with classical networks today. We just switch around between different technologies according to what sort of length scales we need to work with. So currently the Chinese already have in place some elementary quantum backbones between Beijing and Shanghai, and various other local local network hubs, and they're certainly seeking to expand that very rapidly. Now, this one is going to seem a little bit far-fetched because it doesn't really have a classical analog. Any of you who have taken any subjects in classical networking theory, your lecturer might have asked you the question, what's the highest bandwidth way that I can transmit, say, a movie from, or just get arbitrary bandwidths from, Chicago to New York? It turns out that the correct answer, if you are only interested in bandwidth, is just to pack a truck full of DVDs and send it along the highway. No current a 4G network or fiber backbone can compete with a truck full of DVDs. It has astronomical bandwidth. Why don't we use it? Well, it's because of the latency. It's all very well to be able to transmit a huge amount of data from one place to another on a superhighway on a truck, but it's not going to be very useful for making a call like the one that we're doing now, where it has to be real time and interactive. You can't possibly use it for a phone call. So that's precisely why our current networks don't do it that way, why we need something with low latency for real-time applications. What about if it's entanglement distribution, like what we're discussing, where we're not distributing the valuable information itself, but instead transmitting a fixed known type of quantum state, all of which modulo the noise that degrades them, they're all identical. Well, then it's pretty obvious that latency doesn't actually matter. It doesn't actually matter what time an entangled pair arrives between me and you over in North America. It makes no difference because it's the same known state. So one of my colleagues here at UTS, he had this idea for what's called the quantum sneaker net, which is, let's start thinking about that truck or a boat full of DVDs. Let's think about that with entangled pairs now. So we just prepare our entangled pairs. We leave one half of the entangled pair here in Australia, put the other half in a boat, and just ship it over to China or whatever the other country is. But obviously this boat is packed with many, many, many of them, the equivalent of our DVDs full of astronomical numbers of them. Now, whether those entangled pairs arrive now or arrived a year ago and were kept in a good quality memory really makes no difference. Because once I've got it, then I've got my entanglement link, and then I can complete my quantum state teleportation to take my arbitrary state and use the entanglement to teleport it across, and the latency is completely irrelevant. So this idea that sounds completely wacky for any sort of practical classical application turns out when you work through the maths in terms of the final bandwidths that you can anticipate to get on a cost-benefit analysis, this actually works out not too bad. This is a completely sensible idea, and it's an area of research that's being pursued now. So this is called the quantum sneaker net, and that will also potentially, if it materializes, play a role in this big future ecosystem combining satellites and fibers on the ground, as well as these boats carrying entangled pairs. Okay, so now we've got all the bits and pieces that we need to imagine building a big quantum network, just like we do with classical networks. These nodes all represent different computers or sources or whatever in the network. They're connected by communications links, the way normal networks are. These have the ability to transfer quantum information. Now, suppose I want to get an entanglement link between this guy and this guy. Well, now what can happen is, for example, this guy could send an entangled pair between those two nodes. This guy could produce an entangled pair and send one half there, swap the other half with this one, and all of a sudden I've got an entanglement link across those two nodes. And you can reconfigure the network like this using the entanglement swapping. It's interesting that for the same reason as this latency issue, unlike classical information where things really have to go in series in hops, if this was communicating classical information, it'd have to go hop, hop, hop. Well, now we can actually parallelize certain things, because if I've got entanglement between these two nodes, and entanglement between these two nodes, and entanglement between these two nodes, and I want to swap here and swap here to create entanglement from one end to the other, you can do all of these entanglement distributions in parallel. They don't have to be sequential the way classical information is. As long as I end up with entanglement between those three different pairs and then swap them in whatever order, I'm guaranteed to get entanglement between those endpoints. So the whole timing and the synchronicity of quantum information using these entanglement networks, that means that I can parallelize all these things rather than do it in series. So that's sort of an overview of what entanglement networks are. I want to spend the rest of the time talking about now some of the things that we can do with it. And at the very beginning, I motivated all of this by talking about distributed quantum computing. I want to tell you how, first of all, how we can use this for cryptography. So suppose I give you one of these states, now that we've solved this problem of how to get entanglement between different points in a network. What do I do with it? Well, if this is me and this is you, how can I securely talk to you using these sorts of states? So the way to do that is you don't directly communicate using these states. What we do is we use these states, these bell pairs, to generate shared randomness between me and you. So I've written this state as HH plus VV. You might recall that on our plane, we had H and V. We also had plus and minus as some of the different angles that we can have. Mathematically, HH plus VV is the same as plus 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 minus minus. In other words, if they're perfectly correlated along the horizontal and vertical axis, they're also perfectly correlated along the diagonal and anti-diagonal axis. These two states are mathematically equivalent. In fact, I might suggest that, since I overheard you earlier on saying that you were going to be learning about doing different vector transformations, this would be a simple exercise for you to test out your understanding of that. Write out the actual full vector representation for this state, and you'll very quickly see that they are in fact identical. So we've got two different interpretations for the same state. So how do we share randomness between two different points? What we do is we imagine that we've got a large supply of these states between the two different endpoints. And then what we do is the people on either side, Alice and Bob, they randomly, both independently, randomly decide whether to measure along the HV plane or the diagonal anti-diagonal plane. Now, when they both measure along the same axis, the HV axis, they're guaranteed by the correlation to get the same result. If they both measure and ask, is the photon H or V, the other person, if they've measured the same way, they're guaranteed to get the same answer. Similarly, if they both measure along the plus and minus axis. However, if one of them measures in the HV axis and the other one measures in the diagonal anti-diagonal axis, then they just get complete noise and there's no correlation between their measurements whatsoever. The other point is that because they're in superposition, if they both measure along the HV axis, for example, even though they're both guaranteed to get the same answer, they're guaranteed to nonetheless be random, because you recall that this is an indeterminate state. That's what superposition is. It means that it's not determined whether it's H or V, but it's guaranteed that they're going to be correlated. So they both randomly measure in the HV axis or the plus minus axis. They do that as many times as they need to, and then they just openly talk. It doesn't need to be in secret, and just ask each other, oh, which ones did you measure H and V, and which ones do you measure plus and minus? And wherever they agree, wherever they've done the same thing, they're guaranteed to have a random answer, which is the same. And all the other ones, they just throw them away because they can't use it. There's no correlation anymore. And so they repeat this many times. They sift out the ones where they were in agreement, and what they're left with is a big random bit string telling them, well, where these correspond like to the H or V measurements, for example, a big long random bit string. So how is that useful? A random bit string isn't actually sending you a message. That's not very helpful yet. The way that that's helpful is now we go back to classical codes where, contrary to popular belief, there is actually one classical code which is provably secure, as in guaranteed to be secure by the laws of information. No matter how much computational power your adversary has, it's guaranteed that they can't crack into it. And it's called the one-time pad. And the way it works is this, is if I've got a message which is represented as a bit string, so imagine 010101, this is the thing that I want to say to you, hello. And then I've got a key, which is a random bit string, 11011011, okay? So what I do is I add those two together using base 2 arithmetic. So 1 plus 1 equals 0, 0 plus 1 is 1, 1 plus 1, 0 is 1, 0 plus 1 is 1, that's 1, that's 1. So the answer, so for base 2 arithmetic, 0 plus 1 equals 0, 1 plus 0 equals 1, and 1 plus 1 equals 0. It's equivalent to an exclusive OR operation if you've done digital circuits. Now the point is that this is now my encoded message. I decode it by doing exactly the same thing. I do the exclusive OR with the key again. So if I add the key to that again, I get the message out. So the encryption and decryption operations are the same, but it's very easy to show that this encoded message is guaranteed to be secure so long as the key is as long as the message, and it has never been reused. So it's called the one-time pad because you can only use the key once. It's not a very practical code for obvious reasons. You need to communicate a random key secretly with your partner, and you can only use it once, which is kind of just as difficult as just talking to them in the back alley to begin with. So combining that with our quantum protocol from before for sharing randomness, we actually overcome that practical challenge, and now we have a way to securely random, arbitrarily long random bit strings, and we can make as many of them as we want, so we don't have the problem of having to reuse the keys. And now we can implement this one-time pad protocol, giving us perfect security. So this is what's referred to as quantum cryptography or quantum key distribution, where you're just sharing randomness to use as a basis in a one-time pad. And this is exactly what the Chinese have demonstrated using that satellite that I mentioned of. They've demonstrated secure communication between this high point up in the mountains in Tibet and somewhere over off in central China, using this satellite that transmits entangled pairs between them. So obviously that has enormous value to major world governments that want to be able to securely communicate between different points on the Earth. Okay, now coming back to the earlier question of quantum computing. I drew my little diagram. I said if we've got two Macintosh Pluses, you guys probably never had these. These were my first computers. If these are classical computers, you join them with the normal classical link. If these are quantum computers and I want to make them behave collectively as one, I can do so as long as this is one of these quantum communications links that distributes entanglement. And obviously I can't go into the technical details of how that works, but you can take my word for it that entanglement is sufficient to make these two remote quantum computers act as one. So if this was in Tibet, one of the big quantum computers up in a warehouse up on that mountain, and this one was in somewhere else, now they could act, even though they're thousands of kilometers apart, as a single unified quantum device. And of course, this could happen right across the world. At the moment, we have, AWS, they have their big data centers distributed geographically all across the world to create redundancy and whatnot. if I was uploading a big distributed quantum computation to that, the obvious question is, what about the security of that? These are going to be really high value computations that we're going to be doing on this sort of cloud service. It could have enormous military or economic or intelligence value, whatever the case may be. You wouldn't want to outsource a computation to an untrusted quantum computing provider, given the value of some of these computations, which leads on to the question of, is there a way to outsource a computation in such a way that someone else who I don't trust, like a foreign adversarial country, but which has all the quantum computing architecture, nonetheless guaranteeing my security? And that leads on to things called either blind quantum computing or homomorphic encryption, which are closely related, very subtle difference. But basically, the idea is I have a client. This could be me sitting here, a very poor person in a country that doesn't have big quantum computers. I upload my quantum computing to the big quantum cloud, but it has sort of like a firewall that allows me to upload the computation, have it executed, get the result back, and I can decrypt it and get the answer. And even though this guy out here is doing all the computation, he can't know anything about either the computation or the data to which it's applied, either before or during or after the computation. And that's very easily done with quantum computing using these two techniques, which I don't have time to go into the technical details of, but happy to follow up with you guys later on about that. But it can't be done in classical computing. There's really no practical way to do this. With classical computing, when you run something on AWS, there really has to be a certain amount of trust, which is why, for example, the United States military would never dream of uploading its important computations to a Chinese data center, because they're worried that the data will be intercepted. In the quantum case, we can overcome that problem and have perfect security. So the Pentagon could upload highly sensitive decryption algorithms or code breaking algorithms to a Chinese data center and know with absolute certainty that there's nothing they could do to understand the important data that they were licensing out. So we can see now that this entanglement is really a pretty powerful stuff. This is pretty valuable. We can do all sorts of cool stuff with this. And in the same way that the digital information today has huge economic value, all of our multi-trillion-dollar telecommunications infrastructure obviously substantiates that claim that this is incredibly valuable. The next generation of economic value and information isn't going to be in communicating classical bits. That's so cheap now that it costs virtually nothing. I've already sent you guys billions of them by the end of this talk, many billions of them. The real next generation of value in communications technology is the value of entanglement, which is just what's the price of HH plus VV between two arbitrary points on the Earth. This is sort of something of direct economic value in the future, which is going to be driving the building up of these networks. If you find that a particular link between two countries doesn't have enough capacity for distributing many copies of these entangled states, their market price will start increasing, which will incentivize the creation of new links. And so all the normal sort of supply-demand economic models that drive telecommunications infrastructure, they'll apply in this quantum context as well, but where this is the fundamental economic resource. This is sort of our next generation gold standard, the entanglement standard for economics. There's something that's well defined and fixed and infinitely reproducible in principle, but has enormous economic value. So you might imagine that will lead to financial markets where people trade this sort of thing. For example, if in one country there's someone who wants to use quantum computing, in another country there's a provider that can provide a quantum cloud service, then obviously there's going to be a direct market for the ability to access that. And that's done by entanglement links so that you can outsource quantum computations and at the same time do it in a secure way. And these will be tradable, securitized commodities, you could imagine. But it also has big political implications. Let's just simple it down and focus on, say, America and China, okay? Now, we argued before that if both of these guys have lots of quantum computers, if they use them on their own, they get a lot of computational power. But if they were to unify them, then all of a sudden they get something much bigger than the sum of the parts. So at first order, you might think, well, if the United States and China had some satellites for distributing entanglement, it's really obvious from the self-interest perspective of both that they use this to mediate joining their architectures together to make a big distributed one, which is far greater than the sum of the parts, and then just timeshare that between them. That's kind of obvious. That's in the best interest of both. So in terms of a sort of competition versus collaboration, tit for tat sort of prisoner's dilemma argument, it's immediately clear that everybody will want to cooperate rather than compete. That's a good thing, right? Because that drives us towards unification and common standards and working together rather than adversarially. But if you think a bit deeper, there are good reasons why people might prevent that from happening or might allow it to happen for some period of time and then decide not to do it. Suppose one country had more architecture than the other. So the United States was dominant. Suppose China had far fewer of these computers. Now, it might be the case that suppose China wanted to do something adversarial, like crack American cryptographic codes. In other words, running Shor's algorithm, which is one of the ones I'm sure you'll cover in this camp that can be used to crack public key cryptography. Suppose China didn't quite have the quantum computing architecture to run Shor's algorithm in a way that could compromise valuable American assets. But if they were to unify their architectures, they would be pushed above that threshold and they would be able to do that. Now we would have a situation whereby, even though in terms of computational self-interest, as in how much computational power do both sides get, everybody benefits from unification. But there's not really a linear relationship in terms of what the blowback from that could be from an adversary. If you started shifting them over the threshold whereby they can do something nasty to you, you might intentionally say, no, we're not going to be part of that network. We're going to go it alone because we don't want an adversarial party to be able to have the capability to use that power against us. And so this will lead to different sort of game theoretic dynamics in sort of future world politics, whereby at first order, yeah, there's a really good reason for everyone to want to cooperate, because certainly the success of the internet that we're using now has benefited from this idea that we have an ad hoc network that anybody can join and nobody is removed from it, and it works for the collective benefit of everyone. But for the same reason, using the China example, we also know that there are lots of things that they lock out with their Great Firewall of China, because certain pieces of outside information harm what the objectives are of the government to empower them. So this is sort of the parallel to what we'll be seeing game theoretically in future world politics when it comes to sharing quantum resources. So that's sort of more or less the main things that I wanted to talk about. This is a picture, a little cartoon that I made from a book that we're writing that'll be coming out in a few months' time, summarizing what this global quantum networking and quantum computing ecosystem might start looking like, whereby here we've got some individual quantum computers, which is what most of what your camp is all about. But now we've added some quantum communication. This is what the Chinese can do with just one satellite. They're working towards having a constellation to get around to the Earth so that Beijing can communicate with an aircraft carrier out on the other side of the ocean. Other applications that I haven't mentioned, we've got fiber links, the ability to outsource computations and build a wall of encryption around it so that you can do so securely to the benefit of everyone, all integrated with some kind of global marketplace for trading value of entanglement as a resource between different points on the Earth. Here we've got our quantum sneaker net with a boat full of entanglement. This is sort of the vision of where this could really go in the long term, taking the ideas from classical networking technology and trying to extrapolate it forwards into the quantum context. So that's basically the crux of what I wanted to talk about. So I'll just turn off the share screen there and come back to video, and maybe we can open it up for any questions or discussions, or if there's anything else you'd the book is called, it's a very original title, it's called The Quantum Internet. I spent like 6 months thinking up that title. I'll just open the chat so I can read them for you. Okay. Okay. So I'll work backwards since I answered the last one first. The book's called The Quantum Internet. Fascinating. Thank you. Thank you. Does this only work in base 2? No. It can be generalized. It can be generalized to anything that is discrete. So a qubit is just the simplest possible unit of quantum information, because obviously you can't have a base 1 unit of information. So people just typically use 2 because it's simplest. There is a generalization of qubits called qdits. But basically any quantum system, you can just associate the different levels within that quantum system with being different units of information. So if you imagine like the electron energy levels in an atom, they're discretized, there are discrete energy levels, but in principle, there can be as many of them as you want. So you could have a sort of 10 different basis states for an atom if there are that many accessible electron energy levels, but they're all kind of equivalent, and there's no real advantage from a theoretical perspective in terms of thinking in those generalized ways. Okay, so the polarization of photons are possible states and the particle being. So yeah, so the 0 and 1 are the labels that people just adapt from normal classical information, just as sort of what are called the logical basis states. But a logical basis state corresponds to some physical basis state. So in our case with the photons, 0 is H and 1 is V, for example. If you're going to electron energy levels, you might say that the 0 represents the ground state and the 1 represents the excited state of an electron, or in whatever architecture you're dealing with. So 0 and 1 are sort of the abstract labels, and then they get mapped to actual physical layers. And then yes, you do have all the normal single qubit gates for that. So if you've got the polarization of a photon, suppose I wanted to do something that rotates it so that horizontal becomes vertical and vertical becomes down to horizontal. How would you do that? That's just rotating the polarization angle. And there are already simple devices that do this. They're called wave plates that give you rotations of the polarization. And even though these angles are complex numbers, they're not just a simple angle, they're complex numbers. These wave plates correspond exactly to what these generalized Pauli XYZ gates, as well as all the other single qubit gates, are in photons. So there's a direct correspondence there.
We've got some new questions.
Yep. Yeah. Why doesn't big companies like Google build 71 qubit mini computers? Oh, right. The answer is why build a 70 qubit chip rather than 71 qubit chips? The reason is that if they're not integrated together, it just means that sharing the quantum information or the entanglement between them starts dominating the computation and just introducing so much noise. If you've got, for example, atoms in a chip or something like that, they're very, very close. There's very little degradation in the quality of the entanglement between them, and that deteriorates with the length scale. So in terms of minimizing the amount of noise, you want to keep things in most architectures, at least, as physically close together, because then the length scale over which these entangling interactions have to take place is much less. But you're quite right that in the longer term, this is going to become sort of modularized, whereby you know, if you think of a classical CPU, well, obviously we don't put all the individual transistors a long way apart. We integrate it together for the same reason, but for economic reasons, we want to mass produce as many of these little units as possible. So we mass produce heaps of CPUs, and then when we've got a stable CPU, you start networking those together to make a cluster. You'll imagine the same thing happening here. There's some trade-off between how much you discretize things and at what scale and over what sort of lengths. The book should be out in September. If you guys want to ping me on my email address, I can give you guys PDF copies of that. It's free. Okay. Will Shor's algorithm be a useful way to attack computer systems? A quantum internet will be introduced. Right. So Shor's algorithm really only attacks one thing, and that is current public key cryptography, which is RSA, which is what is securing our communications at the moment, as well as elliptic curve cryptography, which is closely related. Quantum computers do not, so Shor's algorithm does not compromise quantum key distribution, quantum cryptography. In other words, although quantum computers provide a way to completely undermine some of the most important cryptography we have today, quantum technology also gives us a way to find a fix for that even quantum computers can't break. And that's kind of the beauty of this quantum key distribution. As I said, quantum cryptography is not limited by any assumption about the computational capabilities of your adversary. It's guaranteed by the laws of physics itself. So there's literally nothing that someone can do unless they discover new laws of physics. Now, I think I missed some earlier up. What is the time span for this ecosystem? Well, the nature of an ecosystem is that it evolves, right? So you could argue that we already have an ecosystem. You can log into the IBM quantum experience remotely from the other side of the world and run simple scripts that do elementary quantum operations and things. So we could argue that that's already an ecosystem. And it's not so much a question of when does an ecosystem exist, but rather at what rate does it evolve. In terms of reaching the sort of sophisticated scale that I had drawn in my cartoon, that's really quite a long way off. It's very easy to draw these things in a cartoon, but some of those engineering problems are fantastically hard. Specifically, if you, like in the example of the constellation of entanglement swapping satellites, if you want to take those two distant bell pairs and swap them by taking two photons and doing an entangling measurement on them, you have to have them arrive at exactly the same time. There's an enormously difficult synchronization problem because we're talking about minute little stability problems. This is an incredibly hard engineering problem when these are moving around the Earth at 20,000 kilometers an hour. Even just on using fiber networks, it's an incredibly hard problem. So the diagram I drew is really, really futuristic. Don't expect that anytime soon, but it is definitely plausible. So touch on quantum imaging and sensing. I'm guessing that probably might not have time to go into that because it's quite a big new topic on its own, but if you want to message me, I can gladly have a chat with you at any time about that. Have I missed anything here?
Yes, I think how is the quantum state teleportation on the world, between points on the world, useful for us if we have to check the correlation classically?
Yeah, so when you say check the correlation the classical way, you mean using the measurements? The answer is these measurements where we do the correlation measurements, these entangling measurements, they, like any measurement, they give a classical output. So when you do a measurement, really what that means is that you convert quantum information to classical information. That's what measurement means in the quantum case. And that conversion process also has the property of destroying superpositions and leaving them in a collapsed state. That's what the measurement collapse problem refers to. Very well covered in the popular literature. So how is quantum state teleportation on the world useful if you have to check the classical correlation, the classical way? So you're actually checking the correlation the quantum way. You're doing an entangling measurement. So it's a quantum measurement, but the output is then a classical information. why is that a useful thing to do? Because once you've converted quantum information to classical information is both cheap, it's effectively free. This isn't costing me a single cent, this entire talk. Whereas if I was sending you a single bell pair, it would cost you millions of dollars based on current prices. So it's cheap. Secondly, it's robust because it's digitized. It doesn't suffer degradation. Basically, you guys are all getting a absolutely perfect copy of the video image that I'm sending you. There is not a single bit of difference by the time it reaches all the 50 different screens that are watching in here. That's how good classical information is. If it was quantum information that was not subject to any kind of correction or protection, quantum error correction, it would be all over the shop. That's why we really like to be able to convert things to classical information. And the quantum state teleportation does the same thing. Once you have the entanglement, you do the entangling measurement, you convert it to classical information, then you transfer that classical information to the other side of the world, which is free, doesn't cost anything, and it's essentially perfect. And then what comes out the other side is, in principle, perfect quantum information.
I think there was just one last question before we should definitely wrap it up. So what implications do quantum networks have on financial markets, for example, high-speed stock trading?
Yeah, that's a good question. We are actually doing some work in this. It will have big implications on future markets, particularly crypto markets. That's the one that it's going to affect most significantly. So if you consider that so much economic transaction these days is shifting over into blockchain-based technologies, how does blockchain work? It's based on this idea of having an irrevocable cryptographically enforced ledger. But the way that transactions are enforced is via consensus algorithms. And the voting there in that consensus is signed off on using digital certificates, and they're based on RSA encryption or elliptic curves, the same public key technology that's used for secure communications can also be used for signing digital certificates. This is how, when you log in to, for example, the your Google Mail, even though you can't see them, you're able to confirm their identity and know that it's them because they sign the transaction with their signature. Now, they are compromised by Shor's algorithms. So quantum computers, in principle, it means that they could invalidate blockchains based on current cryptographic protocols. That's potentially the biggest way that this will affect future financial markets, since so many things are carried out that way, but also more generally, anything which is secured by public key signatures or encryption, which is essentially everything these days, including what we're doing now. So the implications are potentially enormous, and that's why there's a big field of research now called post-quantum classical cryptography, which is to try and find classical cryptographic codes that are not vulnerable to quantum attacks like Shor's algorithm. In other words, ones that are where the encryption is based on completely different principles than integer factorization, which is what Shor's algorithm is based upon. And NIST over in the United States, the Standards Institute, they are currently running a competition to try and standardize some candidate encryption protocols that satisfy that criteria of being quantum proof, but without relying on quantum technology. So not QKD. QKD is not a post-quantum classical cryptographic technique. It's a post-quantum quantum cryptographic technique, but classical is easier than quantum, so it'd be better to do it that way if we can.
All right, we're gonna have to wrap that up, but thank you so much, Peter. That was a really exciting talk, and
great.
These are some great questions. So that was really awesome.
Great, awesome. Thanks very much, guys.